Hi, this is Alex Galt, and I'm looking at a brand new chapter. This is chapter 2, and it's about instantaneous and average rate of change. Instantaneous rate of change is how fast am I going at this very second, at this instant? And average rate of change is, well, I traveled a certain distance, how fast did I go over that time period? So first we're going to look at average rate of change. Average rate of change you should have done before, but it may have been a while. The way you find average rate of change over an x interval, so from x equals a to x equals b, first of all, the way you find the y-coordinate is you plug it into the function to get the y-coordinate. So you can have 2 points on the curve. And notice that this font is uppercase letters, but it's just the way the font is. We're just looking at the x-coordinate a and the x-coordinate b. The way you find average rate of change is you just take the slope of the secant line. The average rate of change is going to be the slope between the two endpoints. We know the slope formula is change in y over change in x, or rise over run. So we subtract the two y coordinates. Sometimes we call it y2 minus y1 over x2 minus x1. And so that slope formula is how we find the average rate of change. The slope formula is also called the difference quotient. You're going to see those words in calculus. That's the difference quotient. So here's an example. The rock's position as it falls is given by h of t equals 16t squared, where h is measured in feet and t is measured in seconds. So what is the average speed of the rock during the first 2 seconds of falling? And so for this problem, what I would do first is I would figure out where is the rock at 0 seconds. So what is the position of the rock when I'm at 0 seconds? So that would be 16 times 0 squared, which would be 16 times 0, which would be 0. So the rock has not fallen at all after 0 seconds. And then I would figure out where is the rock after 2 seconds at the end of its journey. Of the first 2 seconds of falling. So that would be 16 times 2 squared, which would be 16 times 4, which would be 64. And then we're going to do the slope formula between those 2 points. So 64 minus 0 is the change in position, so that's going to be feet. And then 2 minus 0 is going to be the change in time, so that's going to be in seconds. And so our rock's average speed is going to be 64 over 2 feet per second. And you probably really would rather see that as 32 feet per second. And that's the average rate of change of the rock. Another way of thinking about this is I drive to work. My work Edina High School is 8 miles away from here, or from my home. I'm at my home right now. And so if it takes me 15 minutes to get to work, what's my average rate of change? You're going to say, well, I know how far you traveled. I know how long it took you. I just need to divide those two numbers. Okay, so this is the average rate of change. I would like to really stress that at no time in calculus am I going to ask you, when I say the word average, at no time am I going to ask you to add up a bunch of things and divide by how many there are. There's nothing special about t equals 0, t equals 1, and t equals 2, so don't add those positions together and divide by 3 or whatever. At no time am I going to ask you for that kind of average in calculus. That's kind of a statistical average, but that's not what we mean when we say average rate of change. That's going to be the slope. Okay, so that's average rate of change, but how about instantaneous rate of change? Well, instantaneous rate of change, because it's rate of change, we still want to do slope, because when we see rate of change, we're thinking slope. In order to use slope, we need 2 points, but if we want instantaneous rate of change, we want the slope at one single point. So what we do is we take 2 points, and one of the points is going to be at the x-coordinate A, and the other point will be just a little tiny bit away from that x-coordinate. So the distance between these 2 coordinates would be h along the x-axis. And what we do is we take those 2 distinct points and we slide them together so that they're actually 1 point. And if we could figure out the slope of that line at that 1 point, that's called the slope of the tangent line. A tangent line actually touches the curve at just 1 point and has the same slope as the curve at that point. So the instantaneous rate of change is going to be the slope as that distance between the 2 points gets closer and closer to 0. So what we do is we use the magical power of limits from Unit 1, and we say, I would like h to be as close to 0 as possible without actually being 0. So notice that this is still rise over run, and also notice that there's some simplifying that can happen in the denominator because a minus a is just 0. So really, with that difference quotient, our a's wind up just disappearing. And so we have this simplified difference quotient. Notice how if I plug 0 into this difference quotient, I'm going to get 0 over 0. That's the case with limits where we have to do more work. So there's going to be some factoring that could happen to make the difference quotient simplify so that the h drops out so that we can figure out a numerical answer. We hope, right? So we'll do this one. We would like to know the speed of the rock at t equals 2. We already figured out that the average speed for the first 2 seconds is 32 feet per second. I hope your intuition is saying, well, I think at t equals 2 it's going faster than 32. It's going faster than 32 because if I drop the rock, when I first drop it, it's not going at all, but as it drops, it goes faster and faster. So at t equals 2, it's going to be going faster than 32. So we're hoping our answer comes out faster than 32. So what we're going to do first is we're going to find h of 2 plus, and unfortunately, I'm using h again. So I'm just going to call that a capital H. So that would be, oh, lost my page here. So that would be 16 times 2 plus, and we're calling this capital H squared. I'm going to go ahead and square that out. I'm going to make it as expanded as I can. So I get 4 plus, and don't forget there's a middle term here when I square this out. It's not just 4 plus h squared. It would be, and I'm just going to kind of jot this down up here so that you're thinking about this. 2 plus h squared is the same thing as 2 plus h times 2 plus h. So we have to have a middle term. We don't just have 4 plus h squared. We have 4 plus 4h plus h squared. And then we can distribute that 16. So we have 64 plus 64h plus 16h squared. And then I'm also going to find h of 2, which would be 16 times 2 squared. We've already figured that out. That's going to be 64. Now I'm going to do the slope formula between those two. So I have, whoa, didn't mean to zoom in. So I have the limit as h, that's big H, goes to 0, of 64 plus 64h plus 16h squared minus 64 all over h. Notice how these 64s subtract away. So now I have, if I plug in 0, I would have 0 over 0. So that's telling me, oh, I have to do more work. And so the more work I have to do is factoring. I notice that I have a GCF in the numerator. So I'm going to rewrite this a little bit. Limit as h goes to 0 of h times 64 plus 16h. And then all of that is over h. Now I can cancel the h's, so this h and this h can cancel, You can't cancel it unless they're factors, but they are. And now, when I plug in 0, it doesn't give me 0 over 0. It gives me 64 plus 16 times 0, which would just give me 64 feet per second. And again, we expected our instantaneous rate of change to be faster than 32. Turns out it was. It was 64 feet per second. All right, so that's instantaneous rate of change versus average rate of change.